Dear friends, Maths Aspirants is a community of mathematics students, research scholars, and faculties across India, initiated by myself in 2017. As all of you know, this year's NET examination is scheduled in the second week of June. In order to help the students who are preparing for NET examination, we plan to organize a series of online problem discussion sessions. In that series, today we have the first session, which is on the topic of abstract algebra, and we blessed to have Mr. Jayakumar Ravindran, Senior Research Fellow, Institute of Math Science, Chennai, to handle a session on the theory of rings, problems from ring theory. So we will discuss some questions and also some important points from the area of ring theory. I'm sure that it will be very useful in your final round preparations for NET examination. I hope that today's session will be really helpful in your preparations, and I welcome everyone to this program. And I would like to express my sincere thanks and gratitude to Mr. Jayakumar for being with us. And I welcome everyone to this program.
So, as you know, I wanted to talk about rings, and we assigned for 2 hours. My plan is this. Initially, I will explain what is my plan. Then we will go according to the plan. The plan is actually, I split the ring theory into three divisions. That's how they planned in very good books like Dammit and Food, Michael Artin. They planned it accordingly. Our eventual idea in abstract algebra, understanding the polynomial, where the roots are. That's the main goal, okay? To understand them, basically Galois theory, right? Basically Galois theory. Everyone aim goes to the Galois theory. In a way, we are preparing towards that. I already gave 2 talks, and I thank Vijay sir for that. And the 2 talks, I think when we talked about our class, he said that 2 talks will be also shared with you. And please see that thing. It's about group theory. Now we are in the second phase, and group theory is sort of a very nice, mostly everyone from BSc level, even MSc level, even in the PhD level, we explore on that. So there are certain gray areas we don't explore much. And one of the gray area is the ring theory, especially the polynomial ring. What I thought of doing today, I split the ring theory into 3 divisions. Basics, it's all about integral domain. Then we go to the actual the polynomial. But in this talk, I am going to restrict as much as I can basic and the integral domain. In the integral domain, there are 2 big theorems. I always find at least 1 question from this theorem in the part C part, even in CSIR and the NBHM. Okay, so more focused on that. I picked out some few questions which asked in CSIR. Okay, so we will do it. Okay, fine. This is a plan. I go from the basics, and I want you to understand that ring theory is just like everywhere. It's not only group theoretical idea, but ring theory is also everywhere. And I would like to give you 1 or 2 examples where it comes in analysis also, where you can have a very brilliant things out of it. Okay, especially I want to discuss 2 things from analysis point of view, which is continuous functions on 0, 1 and holomorphic function on the D, and which is will cover the basic in a very necessity way. Okay, and if time permits, we will go along, and I wanted to give fair amount of time to ask question, maybe last half an hour, so that we can interact. Then I can understand better about the way I am presenting and teaching. It will improve myself. Okay, shall I now share the screen? And if I share the screen, I may. So my plan, as I said, my plan is very simple. I start from the basic. According to me, and according to my training, we always start from the basic and go slowly increasing. And I know some of the undergraduate students are there, and various part of from India, so it start with a thing. So I understood even in group theory, ring theory, everything start with natural number. Then this is the main thing we have to focus on. Okay, Z, integers. If you don't know anything, sometimes you may not have an idea, right? So you always start from the Z. Okay. So few days before I gave a talk about primes of fields. You surprisingly, this Z plays extremely a big role, understanding in a different way. That's how we used to do in our training. We don't go very traditional way. We always go from a very this part of way. Okay. So we know about Z. Everything start from the Z. So Z is very nice, and you know some of the example. I fairly assume that you know the definition of ring, subring, and the related area, etc. Okay, subring, what is nilpotent element, and some basic things. Okay, so I'm very focusing on this and this today. Of course, this I need to say something about this, and very much I'm interested to go through about this. And as I see many CSR questions being asked from this area, especially if I put 0 and 1. Okay, so in the ring basics, what are the some definition we come along? Ring, subring, nilpotent. Okay, nilpotent, zero divisors. So these are the things. Okay, so these two example I try to pick and work out. And as I said, there are many questions asked in CSIR, NBHM, and ISI exam also. Few of the questions, and this I didn't note down. You can see that I have noted down few questions which are little rare, but these questions are whatever I'm going to write are very fair, and it can be asked in many format. That's why I didn't put it on a way. I didn't write it, but I will tell it. I will tell you. Okay, fine. So first, everything start from Z. We also start from Z. So in a group theoretical point of view, I done 2 videos, and that is there. What I left, what I finished actually, classifying the subgroups of Z. That is, the subgroups of Z looks like NZ, where n belongs to natural number union 0. These are the subgroup, and this is kind of a theme in the first part of the video. Okay, there are 2 videos. You can see that. Now, to do that, okay, so to do that, so there are certain things I had in mind. The fundamental theorem for group theory that says that G is a onto map. This means for onto map, okay, onto or surjective, one can say. So there is a surjective group homomorphism, then G by kernel of phi isomorphic to this one. And through this, in that video itself, the second part of video itself, we classify that every cyclic group either Z if it is infinite or Zn. So this is one of my interview question. One of the institute, when I went to interview, they asked me to classify it. It's either Z or Zn. Okay, and it has also been asked. So this is the part I stopped. Now I like to start from here itself. In group theory, what is the best group that abstractly I'm asking? I'm not asking an individual group. Of course, in individual you can say quaternion, dihedral group, and other things. But in the general way, what is the best thing to understand is cyclic group. This is the best thing to understand. From cyclic group, you move on little bit above and above. You go to P group, nilpotent group, finite abelian group, then P group, then nilpotent group, like that. Similarly, I wanted to go from this. So the resemblance of this theorem is exactly the fundamental theorem for the ring homomorphism. Instead of here, we have onto. We have both the rings together onto map ring homomorphism. Here, GP homomorphism. And the fundamental theorem says that the ring by the kernel is isomorphic to the target. Okay, fine. So now let me talk about, so everything is happening in Z. Now let me talk about Z10. The first thing about Z10, we have to know that, give me a moment, let me add page. So let us recall the basic definitions of zero divisor. what is zero divisor? A zero divisor means I have a ring. So this is non-zero. There exists a B not equal to 0 such that AB equal to 0. It's called zero divisor. In other words, a ring without zero divisor means whenever AB is 0, one of them must be 0. The other way of definition saying a ring without zero divisor means whenever in that ring AB is 0, you have to prove that either A is 0 or B is 0. Okay. So there is a one interesting question. It's from NBHM and CSIR. It's that's why I didn't mention it, because it's being asked in a various perspective, different wording. But essentially the question is that is there a ring with unit? What is unit? In a way, unit means A belongs to R, there exists B such that A be equal to 1. Of course, the ring should have the 1. So there is a beautiful question. Is there a ring with the unit, zero divisor, element, at least element which is not unit or zero divisor? Sorry. Okay, zero divisor. So this is a beautiful question, and this question is asked in many papers in a different variation. In part C, they will ask in one of the part time. Do you have a ring with it has a units, it has a zero divisor, and it has a element which is not unit and zero divisor? First of all, what is the necessity of such question happens? Because we are trying to understand ring theory. Whenever in mathematics, it's better to understand finiteness, then you go for the infiniteness. Okay, am I audible clearly?
Yes, sir.
Yes, sir.
Very good. So whenever in wherever you go in the field, okay, in the field of mathematics, any research area, always better to understand the finite and use that idea and ask infinite thing. Okay, and whatever I'm discussing today, it's being asked in CSIR. I thoroughly researched, and I'm not going anything beyond CSIR. Little bit of NBHM, nothing more than that today. Okay, right? So that you can understand from the base level. Okay. So now it's better to understand these guys first. So Z is fairly little easy. So we fold them for whenever we need it. This is the prototype, but let us go for Z10. First in Z10, there are few things you should know. One, it is finite. Of course, it's a natural number. It's finite. Okay. So better to understand them. Okay. Second thing, A belongs to Z10, either a unit, that is, it is an invertible element, or zero divisor. That is, in NBHM exam, when I think 2018, it being asked, A belongs to Z10, if for any integer, you can prove that it's either a unit or, zero divisor. Suppose if you can able to understand this well, immediately you can draw the consequence that for n equal to prime number, it is going to be a field. That's what we are going to do initially. We are trying to construct a class of example for field, which is going to be necessary later to understand certain things. Okay. Then we post slowly this question into infinite setup, and that's how they set the question paper. I had a very nice talk with Professor Kesavan. He been served as a, I think, long-term NBHM fellow, and most of you may know that. I mean, at least the people who applied before 2020 know that he was the NBHM personality for a long time, more than I think 10 years, and he used to set the South Indian question paper. And he once told me that this is how we used to set the question paper to understand whether the student really understand or not. Okay, fine. So let's go back this. A belongs to Z10, either a unit or a zero divisor, right? So how to prove that? The beauty of this particular ring, it is very visible, concrete. 0 bar, 1 bar, or n minus 1 bar. That is, here the addition operation is called modulo n, multiplication operation. This, what is the addition operation? I add them. For example, in Z6, I add, for example, 2 and 3. It will give me 5. And it will be there, 0, 1, 2, up to 5. I put bar for a traditional reason. It's not necessary if you understand. Suppose if I add 2 plus 2 plus 2, it's 6. Actually, for me, 0. That's how it's a modulo. You add them, always you put the remainder by doing the 6. In general, n. Okay, this is just a Kickstarter. I wanted to just recall the fact. I wanted to prove that it's either a zero divisor or a unit. Okay, so I take a random element. The criteria is very simple. If phi, the GCD between this A and N equal to 1, then it is unit. Or zero divisor. If it is greater than 1, then it is zero divisor. And I think you may not have problem about this Z10. In the basic level itself, Z10, given, right? It is like discussed in the first course of BSc level itself. So I don't. So for some people who don't understand these notations, please be witness. Soon in your course, you will encounter such things. Okay, fine. So in basic number theory, what is GCD? Is the greatest common divisor. If it is 1, it is unit. If it is not, it is not a unit. It's a zero divisor. How to prove them? Slightly, this one is easier. Suppose my GCD A comma N is D and greater than 1. Okay, it's a greater than 1. What is Z10? Z10 is 0, 1 up to n minus 1. You know how to add them, you know how to multiply them. For example, 3 into 3, you will get 9, and you put the remainder mod n. Correct? Okay. So when this one is higher, is greater than 1, I multiply A with the element which is called n by d. So this n by d is strictly smaller than n, right? Because d is greater than 1 and it is going to be here. So when I multiply, it's a legit multiplication. A is inside, n by d is inside. So now let me change it. And this is a common divisor. But for us, n means always 0. In Zn, this n indicates always 0. It's a 0 element. So I'm multiplying with a 0 element. But this is not 0. Of course, I should mention here, remove 0. I'm not talking about 0. I'm removing 0. So A is not 0 and n by d is not 0. But when you multiply, you will get this. This is a very nice number. It is a common divisor, very nice number. So n is multiplied. So I will get 0. So it says that whenever there is a greater than 1, and I have a n by d is a nice number which is inside, then a into n by d is a thing. And I have given you how to find that the zero divisor also. If a is there, you can find n by d. That's the pair. So you multiply them, you will get. So two non-zero number, when I get multiplied, I will get 0. That means it has a zero divisor. So that element is a zero divisor. What if case 2? If d is exactly 1, the GCD is exactly 1. From number theory, in number theory, it is fairly easy to see whenever two number a comma n, GCD is 1. The linear combination, okay, the beauty of this is a linear combination. That is also from a point of view of ring theory, how to find them there. It is called the Euclidean algorithm to find it. But always the GCD is a integer linear combination of those things. That is, there exists x and y such that from number theory, okay, ax plus by equal to 1. So sorry, I used n here, n. So now you have to divide by the thing, no, you have to, this is the number, you have to like divide by and put the remainder. So when I divide by n, what happens that I have a that is already inside the representation inside the Zn. Now x is also, that's why I use bar. It's already representation is there. Now x is putting the remainder, and remember that this is multiplied with the n. Anything multiplied with the n, we always consider them 0. So it's 0, 1 mod m. This is we technically called reading modulo n. Technical terms, reading modulo n. Okay, reading modulo n. When I reading modulo n, anything multiple of n is 0, but this side is 1, so I will get 1. 1 is always remainder, right? So 1 is a thing. This is, I put bar just for notation sake. So this is the inverse. This x bar is the inverse, in fact. You will get only one inverse in the commutative ring setup. Okay. So basically, a element is unit or not. It's just depending on the GCD, right? Now let's come. We have a very good class of example. Take this guy where P is a prime. Always this Z10 is a very nice example of ring with unity. Ring with a unity, and it's commutative. These are the prime examples, and I'm really sorry. In this 2 hours class, it's very hard to bring down the example and explain why it's commutative. I fairly assume that since you are preparing for CSIR, you already knew this. These are the rings examples of ring with unity and commutativeness. Okay, what is one thing lagging in this to become field? To become field, every non-zero should have inverse. But in the case of ZP, any A belongs to ZP, removed 0, this A and this P, always 1, because this is just nothing but 1 bar, 2 bar, P minus 1 bar. It's a less than P. Any A you choose, the representation is less than P. So the GCD is always going to be, because the P is the big in a way. All these are less than P. So it's always 1. So that shows that all A as inverse. Just now we investigated, right? If GCD 1, it has inverse. If it is GCD greater than 1, it is 0 divisor. So only 2 options. Either it's inverse or it is 0 divisor. It's up to us to think. So GCD function is very nice. It is exactly like the determinant function. In the M1 of real numbers or complex number, in general, any field, if you wanted to look at for the inverse, determinant will help us. If determinant non-zero, definitely inverse exists. If determinant 0, no, it is not possible. No, it is not possible at all. Okay, as far as field is concerned. Similar way, the testing function, GCD is a testing function. So it has an inverse. So every A has an inverse. So ZP is a very nice class of field. And in fact, the beauty of this is actually finite field. And this is where you start your studies of field theory. You can study the field theory from 3 point of view: one from linear algebraic point of view, another from polynomial point of view, another classical very nice point of view. Start with the finite thing, then slowly get along with that. So this is going to serve as a very nice examples of field. Now one can ask a lot of questions. Is there only finite field, or is there any finite field which is not ZP? What about this? ZP cross ZP, is it a field or is it even not a field? Then what can we say? Then we can do a lot of questions on this. Okay, there are a few questions being asked here also. So it is also asked in CSR and NVHM. Please note it. This is anything what I'm talking today. It is being asked in CSR, most commonly NVHM. There are certain things which is being asked only in NVHM. If time permits, I will talk. So far we are good. My speed is okay. Everything is okay.
Yes, sir.
Yes, sir.
So
Yes,
let me
sir.
summarize what is be done. Some people may not get introduced this. For them, for a summary, GCD is 1 invertible. GCD is greater than 1 not invertible. That's how in NBHM they ask this question: is there any ring? Or since we do it in finite, is it true for infinite ring also? Is it true? One can ask this question: is it true? Actually, answer is no. And it's very nice to understand this from analytical point of view, right? Since we are not doing regress analysis, I little bit and wave using the graph things. Okay, so this question from algebra point of view also very important. What is this? These are set of all functions. When I put in a real number, it's very nice. It's from two real numbers. And I'm challenging you. You take last 10-year papers of CSIR. At least 8 times this shows up. This particular exam shows up. I'm challenging you. You go and take from 2010 last 10 like 5 years twice the exam, right? Take and you come to me. I will give you my number. At least 8 times this shows up. Okay, but the only problem different wording, and I found that since some students are very sincere, they take it granted the wordings. Okay, they think that these are the way only the question being asked. That's why I don't want to put in the exact words. Okay, fine. So let's do this. CR01. There is a continuous functions from this, and it's very nice to understand two things from the rings point of view. One, let me take let's say A belongs to 0, 1. So let me put 2. This is I'm going to later discuss. IA, that is set of all F such that let me put G also. G such that G at A equal to 0. I am collecting. I fix a point. Let me fix a point 0 and 1. This is A. I'm collecting all the function which vanish at A. Only vanish at A. I mean, it can vanish at anywhere, but definitely vanishing at A. And this is ideal. One is ideal, second is maximal ideal. Now one can ask, is it true that every maximal ideal also looks like this? Exactly. This question I will deal later. That's why I put 2, but I wanted to put 1. It's a basic question. And many people lacking on this itself because they are having problem in lot of examples. Okay. Okay. First thing, look at this example. Just take identity function. What is identity function? 0, 1 to 0, 1. I mean, real. Its ID of x is just x. What is the meaning of unit? In the way, in here, unit means, of course, here is a point-wise operation. So f plus g of x is f at x plus g at x. It's a 2 real number when I put x. Similarly, f into g of x is f of x into g of x. When you multiply 2 function, it is a point-weight. When you addition 2 function, is a point-wise. Okay. Okay. What is the meaning of unit? Here, unit means f is said to have a unit. So there exists a g such that fx into gx equal to, it's not identity. Remember, it's a 1. Point-wise addition is always 1 for every x belongs to 0, 1. And this itself shows that f never vanishes. If f vanishes at some point of time, you cannot get a unit, right? F it is not vanishing. F is not vanishing at all. If f is 0 at some point of time, you may not get 1 always. But look at the identity function. Identity of 0 is 0. So identity of 0 is 0. That means identity function not a unit. In other words, not invertible. Certainly, whenever we see identity, we like zombies. Identity means always, invertible. That's not true. That's why this particular type of questions are important in CSR. Whether we do have a conscious to differentiate this and that. Remember that unit here. That's why I keep on using the word unit. I could have used multiplicative identity. I do not want to confuse you people. That's why I use word unit. The unity, this identity, okay? So the identity function is not a unit because at 0 it takes 0. It is vanishing at 0. So it is not a unit. Now the question, in the last example we had discussed if a function is unit or zero divisor. Is it a zero divisor? If it is not unit, is it a zero divisor actually? So let us understand what is the meaning of zero divisor. I should get a function g. I should multiply with the d. Sorry. And I should get 0 where g not equal to 0, correct? So let us understand from a graphical point of view. That's beautiful. What is identity function? Just like this, no? The identity function means this. Here is 1, here is 1, sorry. Here is 1. This is what identity function, correct? So at 0 it takes 0. We can see that at 0 it takes 0. If I multiply with g, and remember that ID function not equal to 0 if not x not equal to 0, because basically it's identity function x equal to x. But remember, we are in the setup, very different setup. It's a continuous function setup. When I put ID function and g of x, when I get 0, if x not equal to 0, then what? Then g of x into x not equal to 0. So g of x equal to 0 because x is not equal to 0. For every x belongs to open 0, closed 1. So that shows that because of continuity, remember that because of continuity, because of continuous, because g of x is identically 0 for every 0, 1. You know the continuous function, right? In particularly 1 by n belongs to open 0, closed 1. So g of 1 by n is 0. Now take the limit on both sides. Limit n tending to infinity, g of 1 by n is actually g of 0 because of continuous function. So g of 0 is 0. So this is the example, very simple and nice example, which is not a unit as well as which is not a which is not a unit and which is not invertible. So we have an example of a function which is not a unit and a zero divisor. So it's very hard to find such examples, and where to check it, we have to check it. And few more things can be said about, these guys, 0, 1. So when I start this question, let us go here. Is there a ring with a unit, zero divisor, or an element which is not a unit and zero divisor, which I demonstrated? There is a element which just because of identity, just a very nice element, which is not a unit, which is not a zero divisor, right? Very good. Now, indirectly, while talking about this, I also give a criteria for unity. Very simple. Here, when I talked about here, I said vanishing, never vanishing. Never vanishing. So the indirect criteria is any function which never vanishes is unit. So unit if and only if never vanishing. I can give a lot of functions, right? Constant function, everything takes 1. Everything takes 1 by 2. Everything takes this. Everything takes that. And I can put, the translation function, take the identity function, just translate and divide by 100, 200, many things. So any graph which starts like this, which starts like this, which starts like this, which goes like this, it doesn't matter as long as if you don't touch the 0, it is it's a unit. So it has a unit. C of 0, 1 as a unit. What about zero divisor? Do we get the zero divisor? First, I will give you from the graphical point of view. What we really understand by zero divisor. Zero divisor means I multiply f and g. When I multiply f and g, this is also not equal to 0. This is also not, I mean, identically not equal to 0. When I get, I will get 0. When I get multiply, I will get 0. I will give you graphically. Let's say this is 1 and this is 1. Take a function. Okay, let me use a red pen. This is my function. From your school, analytical geometry, how to write, the point connecting equations, how to write equation for 2-point passing through connection, all those things. Okay. So I'm giving a graphical explanation to skip the timing. This is the continuous function at 1/2. And from 2 to 1 is take 0. Now take another continuous function. Let's have a green like this. So this is a continuous function, takes 0 from this place up to 1/2 from here to here. It explicitly can be written, but graphically very nice. Now you multiply. What is the multiplication? Fx gx. Here the x, then okay, let's call this. This is like f, this is like g. When x is here, f is going to be 0. So the total quantity is 0. When x is here, g is going to be 0. The total quantity is 0. But neither f is 0. This is not 0. And g is not also 0. Neither f, g, because it takes some value. See, at 0, it takes 1. At 1, it takes 0. But in the reverse way, f takes 1 at 1. So neither f is 0 nor g is 0. So this set up a very great example of many things. Okay. So are we good? Any questions now? Any questions? If not, say yes, I can continue.
Sir, please repeat the graph of the zero divisor.
Right. Good. So to understand, no, I like to explicitly give you one zero divisor. What we mean by zero divisor, I have to give you a function f not equal to 0. That means in our case, identically 0 means only 0. And I have to give you g not equal to 0. But when I multiply f into g, that should give 0. Graphically speaking, I will give you a function. Take this like this. At 1/2, it's like this. Then 0. So I'm going to write a function which is f. Okay, f. This is 0. 0 less than x less than 1/2. From 1/2 to up to 1. I have to write a function, right? Like this, which connects 1/2. At 1/2, it is 1/2. And so there is a line joining. You can write a function, no? You can write a function. How this line joining 1/2. I just forgot, but this is the thing, okay? I just forgot. So it takes at 1/2, it's 0. After that, it takes 1. So it can be done. Similarly, this is what my f, okay? This is what my f. Similarly, g is from here to its come. Again, the line joining. Then from here, it's 0. So now let me multiply f and g of x. That is f of x into g of x pointwise. And remember, first you have to remember that this is not 0 because it's not identically 0. The g is not 0, identically 0. The f is not 0 here because it's active. It's not identically 0. So g is not a 0 function. F is not a 0 function. But when I multiply, so I can choose, the x I have to choose between them. When x is in this place, f is 0. So the whole product is 0. When x is in this place, when x is in this place, g is 0. So the whole product is 0. When x is in this place, this place where f is active, but G is 0, right? This is the G. This is the G. So G is 0. So F is active somewhere, but G is 0. So when I product it, it's always 0. But neither F is 0 nor G is 0. Is it clear now?
Clear, sir. Very clear.
Yeah. So these are the places we have to think. Okay. So let me pause a brief moment. We have very great professor in our institutes. They used to say some quotes at some point of time when you attend their classes. Rarely they say. One of my professor, D.S. Nagaraj, told me personally, the richness of in math is measured how many examples you know. It doesn't matter what area or how little area you know, but how many examples you know, right? So you have to know this kind of examples. Okay. So these are the basic I like to cover. And in this basics, you know, so far what we covered in the basic, what is ring, what is subring, what is, this and that, zero divisor, nilpotent element. Now, I didn't talk about nilpotent element much. It will be very nice in the matrix ring, not here. It will be very, very nice when we talk about matrices. Okay. Okay. So far, in a finiteness, we dealt with Zn. Now, C01. Okay, for someone who attended complex analysis, for them it is going to be easy. For who don't really attend complex analysis, please, these are something that makes complex analysis so beautiful. I like to talk about this one little bit. If you don't attend complex analysis, believe me, complex analysis is something really beautiful because of the analytical function. This I mean, okay, this I mean F from the unit disk to unit disk analytic. Analytic means is differentiable at a point and there's also some neighborhood of the point. D means unit disk. Graphically open, okay, remember that open unit disk. In the complex plane, it's like this. Inside, not this, the outer. It's an inside only. Now, same question being asked, okay. So let's have the beautiful definition of integral domain. Integral ID, let me put ID. Integral domain means ring, commutative ring with unity without zero divisor. A commutative ring with unity without zero divisor. This is called the integral domain. Example. ZP. ZP is a commutative ring unity without zero divisor. But we are not interested in this. This is fairly easy. And one of the net, twice in the net exam and as well as NBHM, they talked about this. Holomorphic function on this, okay? Holomorphic function on this. They talked about this, really. That's why I like to give you, there is a beautiful theorem called identity function theorem. In complex analysis that says that suppose I have a function from domain to complex number analytic. If f is 0, f is 0 on some subset of, let's say L of D, which has limit point, then f is identically 0. That is, if you have a function which is vanishing at some subset, so looks like a domain like this. This line is a subset and which has a lot of limit points. If in this line it vanishing, then it's done. The f is vanishing everywhere, and this is called identity theorem. For certain reason, This is called identity theorem for many reasons. Okay, it's better to have this version than the two function version. But what we want actually two function version. This set of all holomorphic function is one of the beautiful examples of ring, which shows up in many places, especially in complex analysis. Extensively study done on these places, many PhD done on these places to get a very nice domain and classify their homomorphism, how it is algebraically. But for us, abstract algebra, it's a very nice ring and it's actually integral domain. Harm is integral domain. But C of 0, 1 is not integral domain because we showed there are some zero divisor, right? We showed there are some zero divisor, but harm is actually a integral domain. How it is integral domain? Because of this theorem. When I multiply two function, okay, when I multiply two function, when I get 0, right? When I get 0, then one of them must be 0. I don't want to go into that because it takes too much of time to understand from complex analysis point of view. But try to understand. If you know complex analysis, it's fairly easy. If you don't, it's fairly beautiful because later on you will find this theorem very beautiful and surprisingly you are going to use. Okay. Okay. Let me pause a moment and ask this question. It's a very simple question. Take Z. Everything starts from a Z. Give me a field which contained Z. Z is not a field because 2 has no inverse. But please give me a field which is containing F. Tell me a field. Yes.
You're asking field
Q set of rationals, set of reals, and set of complex numbers.
Somebody said Q. Then, I mean, how many of
R
you
and
thought
Q.
immediately Q? Yeah, of course, there are real number, there is complex number. But how many of you just ask yourself when I said Z and give me a field, how many of you thought about Q immediately? Many, right? Many people. I hope many people, because I lively experimented in my classes, hundreds of 100 people. I lively experimented, and you know that none of them say to me it's R or C or some. No, nobody said like this Q root 2. Yeah, of course, this contains that, this contains that, this contains this contains this contains this contain. But there is something indirectly we have a feeling. To make it precise, whenever Z is there in some field, automatically Q will be there. Some copy of Q. Because you see that the field means what? Every non-zero element has an inverse. That's a beautiful property. So every integer other than 0 as the inverse means that's actually the Q. In some way, Q is minimal. Somewhere Q is minimal. Okay. Somewhere Q is minimal. That is, whenever Z is inside some field, automatically Q is also inside the field. So it's not just Z. Z comes with a pair of Q. Z always constructed within the Q. Okay. Similarly, there is a beautiful theorem and the end of the basicness. This theorem ends the basicness, and this is also important. One beautiful question being asked, and I want you to leave with the question, pondering on that. Every integral domain. Okay. Why I am writing this clearly, even not putting ID, because it is a statement being asked in CSIR. In the part C, that this is the one of the option. Pick out the right statement or true statement. Every integral domain can be embedded. I'm not sure about the spelling. Embedded into a field. So this is a theorem which ends like kind of ends the basic. One of the CSR question: is it true every integral domain can be embedded into field in? Yes. Given any integral domain, commutative ring with unity without zero divisor, let us take R. There is always field. So that denoted like this. Damit and food book. I think many books they denoted. Okay. In a way, it is minimal. Means whenever there is a copy of some other field, automatically this FR will go inside to the E. Like that. That's what I explained. When Z is in the some field, some copy of Z integer sitting there, automatically Q will go. And this is where one should end the basic for BSc student. And this is how generally in the all of the universities, it's very hard to complete it, but this is how the basic should be end. Okay. Now the question, it is your turn to go and search. Question. What is that field? Harm D. That is, the people who know complex analysis, can you tell, is it true? Every holomorphic function can be expressed as Taylor series. Is it possible? Especially in the unit disk. Is it true? Every analytical function or holomorphic, both are same. Regular function, both are some different name. Regular, analytic, holomorphic, everything is same in the complex analysis. Is it true? People who knows complex analysis, please tell me the answer.
Yes, sir.
Yes. So basically, this one is a collection of Taylor series, right? This analytic function means basically collection of Taylor series, right? Now my question is, did you read anything other than Taylor series in complex analysis? Have you encountered any other series?
So Lawrence is
Exactly. So that Laurent of D is actually filled. And that guy is containing this. Every Taylor series is a Laurent series, right? So you will find that this is something very beautiful. Something happening in algebra which has a deep connection with this. So Laurent series is actually a field which is actually containing this. When you go from algebra, when you see these proofs, you will understand that how beautifully Laurent series pop. That's why it is very beautiful to connect the subjects. This is just for understanding, and also it is asked in the CSIR. It is asked in the CSIR. What is the field completion? Not the exact word. They use a very formal and nice word, and this is asked in CSIR. And again, telling you anything what I talk here is in the CSIR, maybe in the NVHM little bit. Okay, and you can always find. And I'm dare you to challenge. I'm challenging you. Go and find anything which is not from CSIR in this class. Okay, so this is the end of the basic. Once it's the end of the basic, I told you I finish like split this thing into basic, all about integral domain. Within the integral domain, then one can go for advanced. Advanced means polynomials. If you are able to understand about polynomials, what are the things in polynomials? Irreducibility. Basically, the irreducibility. How those are connected towards our previous thing, right? Then you can go for field theory. That's how the field theory started, and eventually the idea field theory along with Galois theory. That's the aim of algebra. Once you finish that, the algebra goes in a many directions. Algebraic geometry, commutative algebra, representation theory. Those are research areas which goes deep. But initial up to MSc level, everybody should know about Galois theory. So Galois theory is the heart of algebra, and the idea is so beautiful. Okay, I don't know how young Galois found it. Within 19 years, he done everything. Okay, so far are we good? Can we go? And it will be very nice if we go and see in internet math stack exchange how this Lawrence series becoming a field of this. If you are interested, really, there are something for a BSc student. This can be a project. You can take this as a project. Okay, so let me stop in that way. So before going to the next level, what is the next level? I'm going to talk about only focusing on integral domains, because every integral domain there is a field, right? So eventually my idea is goes to field. I done group theory, now ring theory, then I go to field theory. So I have to prepare. So that's why I'm trying. So before jumping into that level, is it okay? Like, can I go, or you have any doubts in this itself that I can solve? Yeah, please talk little loudly.
Sir, can you hear me?
Yeah, you are audible. Yes.
Sir, actually, first of all, first you can ask me question, sir. Is there a zero divisor or
Is there any ring
is there anything with this property?
which contains three kind of elements? It has a unit also. It has a zero divisor also. It has element which is not unit and not zero divisor. Yes, there is a ring, no? So this,
yeah, 0,1.
yes.
Yeah. But Zn is not the for Zn it will not work, no, sir.
This is not an integral domain because it has zero divisor. Yes. That's your question.
Yes, sir. For that question, what is the answer? Yes, is the answer.
This is the answer. It has a zero divisor. It is as a unit. It has some element which is not zero divisor, which is not, which is not a zero divisor, which is not unit. But in Zn, it is not like that. Zn, always the element either zero divisor or invertible. That means unit. It is unit or zero divisor. But this kind of rings are very interesting, also complex. That's why one should focus on these rings alone. It can be not generalized. So it has zero divisors, it has units, and it has some element which is not zero divisor, which is not unit. So it is very uncharacteristic. Anything you talk about the units may not applicable to them. Anything you talk about zero divisor may not applicable to them. So it is very hard to go further, right?
Sir, sir, can we conclude like this? For finite, it will not. It does not. And
No, I'm not saying that. There are finite rings. There are finite rings that also, sort of need to be studied. It may also have an element which is not zero divisor, which is not unit. I didn't say that. There are finite rings. Even if you go to non-commutative setup, matrix rings are the very best rings to understand because of linear algebra, where itself we have a lot of problem. Matrix ring itself, we have lot of problems. The power of linear algebra, we have the power of linear algebra. Still, we have a lot of problems. So that's why commutative setup is a much better setup. Okay. Any other questions from others? Or may I continue? May I continue?
Yes, sir.
Okay.
Yes,
So far, what we done? Let us summarize. We wanted to understand the basic. Basically, I wanted to recall them fundamentals. So, what is zero divisor? What is unit? What is a not zero divisor? Not unit. And I want to also call nilpotent, but it's need to be discussed in a different point of view because it is really beautiful in the matrix setup. If I get a time, I will go through. But all these basics are set up because I understood from sir there are BSc students and I don't want to scare them. Certainly, I wanted to give the hint that in the future, if they continue mathematics, they will come across beautiful things like this, right? So that's my aim. Not scare them as well as not spoon feed them. But MSc student who want to be a net aspirant, national eligibility test, they should know this, right? Because they soon become a professor or a PhD scholar. Okay, so let's go to the next level. What is the next level? Now I restrict my focus on a very nicer class of rings, which are called integral domains. And what are the best integral domains? I have this. Few questions I have this. See, the field are the nicest integral domains, then Euclidean domain, then PID, then UFD, then integral domain, then commutative ring with unity, that is CRU. Fields integral domain, PID, UFD, ID, integral domain, commutative ring with unity, general domain. So here the MNs will come. M1 of R, M1 of F. These are the things come. Here C01, Riemann thing. Okay, C01 Riemann thing. In generally C of X. In this L of, if you know about Lebesgue, this will come. In the internal domain, Z will come, of course. Z will come here also. Z of X will come here. Z of X will come here. F of X will come here. So now there is a question. Do we have, so for example, real number here, ZP is here. Do you have an example of field which is not a Euclidean domain? Do we have an example of PID which is not this? Those kind of things are there. Especially today, I want to talk about PID. I will tell you why I like to talk about PID, not ED. We will start from the scratch. But before that, just have a look. These are the questions, typical questions being asked in CSIR, right? Okay. 2 questions. Well, there are 3 questions, of course. Whatever I said, apart from that, this one is that what I'm going to do, I'm going to share this PDF to you and I want you to do it. Try it. If you're not able to get it, sir will share my, the WhatsApp number where you can ask just for this question's sake. Okay. In the WhatsApp, you can ask. And I'm sure that if you're able to understand them, you can do that. Okay. For example, we have this question: are we a finite non-commutative ring? Non-zero commutative ring with unity? Then which of the following true? So there are questions. Any non-zero element of R is either a unit or divisor. It is not true, right? Because we have example C01. In C01, there are units, there are not unit, there are elements which is not a unit, not a zero divisor, and they are challenging that everything. But I'm wrong. There is a word is finite. Now we have to think about it. We have example Z10, it is true. It's either a unit or a zero divisor. Do we have example? That's where I want you to check. Okay. I so far talked about Z10. Now the question, is there a Z10 only? Do we have anything more than Z10? What about Z2 cross Z2? This is a ring, no? This is a finite, and it is not looks like a cyclic. As far as a group theoretical comparison, it is not cyclic. That's why I put this question before. You see, the two field cross product is actually a ring. Is it a field? One can ponder over that. Try to solve this kind of question in order to get the hold over the basics. So I want you to do these questions because I'm not going to write the exam. You are. Okay. So this kind of question about maximal, ideal, and all those things comes. So before going to the next level, I'm going to talk about PIDs. Let me restrict myself to ID. I'm going to talk about internal domain, that is CRU, commutative ring with unity without the zero divisor. That is AB equal to 0 implies either A is 0 or B is 0. This is the element. Either A is 0 or B is 0. Okay. Okay. And there is a beautiful theorem. This is a result many people must have heard that. What is a beautiful theorem? I is ideal in R1. I by R is integral domain if and only if I is prime ideal. Second, I by R is maximal if and only if I is field. If and only if I is maximal ideal. Okay. So this is a beautiful thing. I have to explain the theorem as a statement. It's okay. I just state the statement, but I have to give you very nicer examples, right? So let's go to have this example. Again, prototype example, Z, Zn. So let us start with Z. I have a 0 as ideal. 0 is one of the ideal. When I quotient by 0, I get again Z. That's nothing. So I know that this is ID. So this is prime ideal. Prime ideal. And I'm again assuming that you know the definition of ideal, you know the definition of prime ideal, you know the definition of maximal ideal. If you don't know the definition of maximal ideal, take as a this is a definition under this setup. Commutative ring with unity, this is a definition. A maximal ideal means the quotient space is thing. Okay. Now Z by NZ. That is a precisely notationally same. And we know that, right? We know something. This is field. If and only if n is prime. Not even integral domain. If and only if n is composite. And in the basic, I restrict myself. I'm really resist myself to tell this. And anyone who starting the ring theory come across this result. Result finite integral domain is field. Finite integral domain always a field. So there is no question. Now one can make up a question. Is it true that every integral domain is a field? In the set of infinite level, not true. We have Z, the number 2 or number 3 does not have any what inverse, correct? It has no inverse. So that's how people set up the question, okay? That's how people slowly set up the question. They talk about the finiteness, then they ask about infiniteness, okay? And from that we can say that when the n equal to p, so this p is that actually a maximal ideal. So as far as prime ideal concern, 0 is a prime ideal and p is that. For maximal ideal, p is that. And you might have wondered, some people might wonder, why also you are considering a prime ideal? Yeah. Because every field is integral domain, right? Every field is integral domain. That is also there in the basic level. Every field is integral domain. I already recalled. Every field is actually integral domain. Or I put it here. The integral domain consists of many things. Okay, fine. So this is the nice things I wanted to use. So our prototype is Z and Zn. We talked about Z and Zn prime like easy. Now I should talk about C of 0, right? I should talk about P of 0 so that we could have a good examples. So let's talk about C of 0. I stated like this: IA, set of all functions such that f at A equal to 0 and A belongs to 0, 1. I'm collecting all the functions from the continuous functions of 0, 1, which vanishing at A. Remember that only at A. I'm not saying that only at A. It may vanish more than a point, more than A. It may be vanish everywhere like a 0 function, exactly the 0 function. But I'm collecting whenever a function as a root at A or the solution at A or vanishing at A, I'm collecting. My claim is actually IA is maximum. Now I'm going to give you the trick. To prove that directly, what I need to do, to prove this directly, I have to show first this is the ideal. Remember that to do it, I have to show this is the ideal first. Number 2, it is maximal. Some definition there for maximal, right? No other ideal which contains this is either itself or the whole, like a prime number. So I have to go in that way. Not, I don't want to do that. Instead of that, I'm going to give you a trick how to do this. That's how I told you about the first fundamental theorem. Here, I talked about the fundamental theorem. if I give you a ring homomorphism between two rings, which is onto ring homomorphism, then R by kernel is isomorphic to this. So the R by kernel is isomorphic to this. If it is happened to be the field, this kernel becomes a maximal ideal. So in the basic level, everyone come across in the group theory itself. This is a normal subgroup, but here it's like a ideal. If it is a field, then we have a maximal ideal. That's what I'm going to do in our case. Okay, let's do it. So can you guess, can you see any field underlying somewhere in this question? Look at the only question. Can you see any field underlying? Can you feel immediate field? Somewhere some field. In the write-up, can you see any field? Am I audible?
Yes, sir.
Yes, sir.
Can you able to find some field? Whatever written, can you able to find a field? What field apparently playing a role underlying? A real number, right? This guy. A real number. So this is a trick. Try to learn this trick. This trick works in group theory, ring theory, field theory, apparently linear algebra. This is a trick. You have to be so concentrated about this definition. So concentrated about this definition. I am going to give you lot of examples. The moment you change, many questions being asked from this area. Okay, be careful about this. Real number is a field. I'm going to do what I'm going to do. In the codomain level, I put real number is a field. In the domain level, I'm going to put 0, 1. I'm going to define a ring homomorphism. What is a ring homomorphism? Which takes as an input the function, output just a real number at A. For simplicity, we take the A also 0. So for apparent reason. Evaluation at 0. Some people will put like this. So better to have A because of this definition. Evaluation at A. See, this is the ideal I'm talking about. This is the definition I'm concerned about. I'm taking a ring homomorphism. Check it. Check. This is a ring homomorphism. Check it. This is ring homomorphism. Also onto. It is actually onto ring homomorphism. Try. If you are convinced yourself, for now, put the trust on me. Let's go further. I have a ring homomorphism from here to here, which is onto. Then what happens? By first fundamental theorem, this by kernel of this phi isomorphic to real numbers. So this is a field. The side is field. So this is a field. So that implies kernel of phi is maximal. So as we are in the final preparation round, if you are able to follow this group, the mass aspirant group, you must have come across a lot of YouTube videos of the old videos from the people, also discussions. I'm sure that most of you comfortable with this definition. R by I is a field if and only if I is maximal ideal, integral domain if and only if prime ideal. So that's what I'm using. But what is the definition of the kernel? Kernel of phi is a set of all function such that phi of f is actually 0 element in the real number. But what is the definition? This is evaluation at A. That is f at A equal to 0, which is exactly IA. The definition of, look at the definition of IA. IA is set of all function vanishing at A. The kernel here, the definition is this one. And you may ask me, how do you can come up with this idea? This is not a, the unusual idea. If you are little bit of aware, this idea is being used in many places. I can give you at least 5 examples where it's being used. So for the moment of confirmation, let us pause the ring theory, the same question being asked in another place in linear algebra. I wanted to have this idea. Okay, in linear algebra, there is a beautiful question which is in CSIR 6A. 6A, okay, belongs to M1 of R. 6A belongs to M1 of R, which has a property such that A and another matrix is 0 implies B is 0. That is, whenever AB you multiply with 0, you will get B equal to 0. Prove that. I'm not writing exact word. Prove that A is invertible, right? So forget about this for a moment. I wanted to make sure that this idea, it's in ring theory, it's in group theory, it's in field theory, it's in representation theory, it's also in linear algebra. At least I wanted to give you one example which is outside of ring theory. The same idea, right? Okay. I mean, defining the homomorphism idea, defining how to define the homomorphism and make use of it. Apparently, when you see this first question, I'm giving you the answer also. Prove that it is invertible. When I see this first, I don't have any idea. Like, I have a A, which is a M1 of R. In fact, I can put it not even M1 of R in general. It's a n cross n matrix over a field. It has a property. Whenever I multiply B and getting 0, when B becomes 0, it's kind of an integral domain property. Kind of. I'm not saying exact. Kind of integral domain property. So can you prove that A is invertible? Now, let's have a little discussion. How one can approach? How do you approach? I will tell you the technique, but tell me, initially, if you see this kind of question, try to prove. How do you approach? This is asked in NBHM also. Exactly. In exact words. NBHM in the olden time, they used to have this written exams. I think IISc or NBHM, I'm confused, but there is a written exam. ISI? I don't know, sorry. But it is being asked in that way. Any idea to attack this problem? Just try guess.
Can we take determinant?
Okay, very good. That's the first thing everyone should do. So take the determinant. Okay, determinant of A, B, then what you do? That's a very good approach.
That is equal to determinant A, determinant B.
Okay. And you will get determinant of 0, which is 0. Det of, 0, 0, finally 0. This shows that either det of A is 0 or det of B is 0. From that, how do we get that? If you are able to prove that determinant of A is not 0, then invertible. Very good approach. But you will have a problem. I'm sure that this is the first approach everyone should do. From that, how do we conclude? Yes, very good approach. But is it possible to conclude that the determinant of A is not 0 from apparent to this?
It's given B is 0.
Okay. If B is 0, the determinant is 0. But that doesn't mean that, determinant of A is always 0, right?
Since A belongs to Mn of F, determinant of A is belongs to F.
Correct.
F is a field.
Right.
So it is integral domain.
Right. That's okay. In the integral domain, if you know one of them non-zero, the other one is non-zero. But here we know one of them always 0. Determinant of B is always 0. It's 0. How do I conclude the determinant of A is not 0 from that? That's the question. That's very good approach. You have to feel the poverty of this technique. This technique is not enough. Then you have to go. One student approached from rank idea. He wanted to prove A is full rank. He tried and he was very close, but he's not able to do it. So think about it. This technique is not working.
Sir.
But yeah, yes.
Sir.
Yes.
We can do in this. If I suppose it is invertible, then means I can reduce it to Echelon form.
Right.
Then I'll be having
What are
something
you
like
assuming?
upper triangular.
What are you assuming?
If I assume A to be invertible, non-invertible,
that's what we want to prove, no?
we have to prove A invertible, right? Sir? So
Right.
I'm assuming A is not invertible.
Okay, A is not invertible then.
So its rank will be less than n, no? So using means if I reduce it to Echelon form, then
Right.
means I will have n minus 1 non-zero row, and it will look like
Right.
something.
Yeah, you can
It will look
apparently
like
set
upper
a B.
triangular matrix.
Right, you can apparently set a B so that the final row, at least the final row is non-zero.
Final row
You
will
can
be
set
zero.
up a B which is not zero when you multiply this zero. But the question is that
Yes, sir.
how do you expect the row echelon form respects the multiplication? Basically, row echelon form is a changing the basis. It's a linear algebraic idea, right? Changing the basis that don't respect the multiplication. But this is also a very good approach. You are saying that you start from A, then reduce to low echelon form. Definitely, if it is not invertible, the final row is zero. Apparently, we can set up, the B. Then that row echelon form and B is not zero. Now the question is that how do you go back to the original A? The question is about the original A. Can we get this B when you go back? The origin different B that's non-zero. But a very good approach, contrapositive approach. Okay. So now I think I have to tell you the technique. So the technique is a homomorphism technique. So this technique is a very universal technique. It's not apparent. That's why you need people like, experts. I also didn't know about the technique. My seniors told me this is a technique. From M1 of F to M1 of F, define T. Okay. Let me put A. TA of the matrix B, any matrix B, AB. This is a linear map. This is a linear map. It's very easy. Using the matrix property, you can do it is very easy. This is a linear map. Once this is a linear map, okay, what is a kernel? Look at the kernel. Kernel of TA. What is a kernel? I'm collecting all those B such that TA of B equal to 0. That is AB equal to 0. But what is the condition? AB equal to 0 only if the B equal to 0, right? The only possibility B equal to 0. So I will get 0. That implies 1, 1 map, correct? Up to this is clear? I'm defining a linear map. The condition is given whenever you multiply with A and B, you get 0 means B is 0. I'm checking the kernel. Kernel is singleton. Am I sure this is correct?
Yes, sir.
Now use the rank nullity. Rank nullity. Rank nullity says that this is onto also. Same rank, 1, 1 map. This is onto also. If it is onto, what does it mean? It is onto means identity from the codomain. Codomain. As inverse. What is the inverse? There exists a B such that, let me put B naught maybe. TA of B naught is actually identity. But the definition is A B naught. So it has a right inverse. But basic linear algebra tell you that whenever there is a right inverse, automatically left inverse, both are same, right? In fact, one of the CSR question is that every inverse of, suppose A is invertible, inverse of A can be represented as polynomial in A. This is one of the questions in CSR and one of the beautiful theorem. The inverse of A can be written as a polynomial in A. I'm not doing linear algebra, I'm not concerned about that, but see about the technique. This technique is suddenly magical. So there is no when you see it, apparently you don't get the idea. That's the reason you should attend this kind of talk. And it is now free because of people like Sir Vinod Sir, right? This is the reason you should attend. You know the technique. Many people suffer without knowing the technique, but you know this technique. But when you look at the problem, you don't know the technique. Apparently, I don't know the technique. I got from my seniors. Suddenly, you define this thing. Now you know this technique. You can use this technique along with that. In a way, this same homomorphism will applicable of the one of the theorem I mentioned today. What is the theorem? Finite ID implies field. If I wanted to prove just 2 lines, I can prove. What is the thing? 2 lines I can prove. Like this. I take A from the integral domain, finite. This is work because of finite. See, this is work. Rank nullity theorem I used. Okay, this is work because of the finite dimensionality. It is not true for infinite dimension. Now remember that. Try to remember that this is not true in the infinite dimensional setup. Finite also is being used here. Finite integral domain is a field. I wanted to prove field. In order to prove field, only one condition is missing: non-zero number having inverse. I wanted to prove non-zero number having inverse. What I'm going to do, I'm going to use the same idea. I am defining a map from R to R like this. Phi A of X is just AX. Check. This is GP homomorphism. I am in the ring. I'm not claiming this is a ring homomorphism. I'm just claiming this is a group homomorphism. Check. Try. Once you know about this, okay, once you know about this, then you know if you are like, trust on me, look at the kernel. What is the kernel? Set of all x such that Phi A of X is 0. That is same as saying Ax equal to 0. And I have taken A non-zero. Remember that. I have taken A non-zero. If A is non-zero, because of the integral domain, X is 0. Because of ID. Because of ID is X is not 0. X is 0. If it is X is 0, it's a singleton. Right? Singleton. If X is 0, it's a singleton. Then what? If X is 0, it is a singleton, implies map is 1, 1. If map is 1, 1, that is map is 1 to 1, kernel is singleton, map is 1 to 1, ends on to. Because of finite. Remember that both sides is of same set because of finite. Then 1 belongs to the codomain. As inverse. That is, there exists a x naught that is equal to 1, but that is nothing but A x naught. And we are in the commutative ring, right inverse, left inverse, same. So A has a inverse. I'm trying to tell you, this is there in the book, Damit and Ford, R10, Ian Astin, Topics in Algebra, Ian Astin. This is not a new technique. Only thing, how to use the technique for us. This is a theorem in the book. But this kind of techniques are there. It's coming, right? So it is the thing. We have to use the techniques. That's why book reading is so important. Theory is also so important. As well as problem is also so important. Okay. So the technique is not new, but the only thing is new how to use the technique in the different scenarios. I have a lot of examples in the field theory also. There are certain examples of this kind of things can be done in field theory. Okay, so these are the things. Okay. So Vinod sir, can I continue a little bit and question section for 15 minutes, or maybe stop and ask for question section?
Yeah, Jay, you can continue for 10 more minutes.
Right. Okay, that's good. Okay. So 2 big theorem I wanted to talk about, just result that will be helpful for you in the setup of this field Euclidean domain. I told you I like to talk about PIDs. This is a 2 big theorem. Try to understand the result. Eventually, we are preparing you to understand the polynomials. Polynomials are going to be big complex. because of the degree 2, degree 3, quadratic, quintic, and much more degree. The higher the degree, more complex. So single degree means linear. We have a linear algebra to deal with them. Multiple variables is also fine as long as if you are in the setup of linear algebra. But the moment if you go further, you will have a lot of problem. So eventually we are preparing for a thing. That's why the PID. And PIDs are very nice. Okay, if I ask you the question, let's ask this question. Abstractions. I'm not asking a particular example like quaternion or this and that thing. There are general definitions, no? What do you think about which group is very easy to deal? It's a class of group. I'm not asking about one particular group like dietral or maybe you can say Kleinfeld group. No, not. I'm not asking that. In general, what kind of group is easy to handle?
Cyclic groups.
Cyclic group.
Very good. This is what I expect. Cyclic group easy to handle. Then little harder is abelian. Little harder is actually the nilpotent. So what is the cyclic group? Cyclic group is generated by a one single element, right? That will do everything. So I translate the definition in the ideal way. If I have a ring where every ideal generated by one single element, it's called PID. See, the help of the understanding of a group theory helps. Every ideal is generated by a single because I don't want to make it complex. Okay, I don't like to make it very complex. So I always wanted to make sure that things are easy. So let's start with the things. Already I have done enough theory. Now it's better to go for the next level. Whenever I start the next level, do the same thing. Simple. Start with the simple. PID are the exact translations for cyclic. For me, I would say the PIDs are the exact translation of the thing. So there are two things. First, as I said about the class, we are suffering because of not having many examples. We are poor. So I have to give you a lot of examples. Okay. So this theorem is going to help to get examples. F is field implies Fx is PID. Principal ideal domain. That is, every ideal can be generated by one single polynomial. Eventually, we are preparing for this only to understand the third part of ring theory, understanding this only. Fx. So every ring is actually, polynomial ring over a field is actually PID. In fact, the converse is also true. That's a big theorem number one. Okay, so Z is actually PID, but Z of X not PID. Z is actually PID, but Z of X not PID. Remember that. Because of this theorem, F of X, or let me put R instead of F. R is a field if and only if Rx is PID. So we have an example where Z is not a field but PID, but Z of X is not a PID because it's not a field. So it is not true that from PID you go to the next level, you get the PID. It is not true. It is not at all true. You don't get a PID. Remember, this is one of the. I also included few questions to work out in the level. So what are these are the question? Okay. So the first question you see that Z of X in the CSIR December 2016 they asked, is it Z of X is a principal ideal domain? Not true. In order to become a polynomial ring over any ring to become a principal ideal domain, the underlying ring should be filled. The underlying ring should be a field. Okay. Look at the C. R is a principal ideal domain and P is a non-zero prime ideal. Then R by 3 is finitely many prime ideals. Those kind of questions also relevant to this kind of discussions. Okay. Anyway, so let's go back to this. At least we have an example. A PID were not the ring. Okay. So fine. So let me continue. This theorem is going to be helpful in many places, but the next theorem also something called Gauss lemma. R is unique factorization domain. Please, if you don't know about the definition, look at the internet and get the definition. This theorem it says that if and only if UFT. So just focus on this. Every field is a ED. Every ED is actually PID. Every PID is actually UFT. Every UFT also is integral domain. But what about the converse? Is it every integral domain is actually a UFD? No. There are integral domain, those are not unique factorization domain. There are unique factorization domain which are not PID. The example is this. Z is PID. That implies UFT. Every PID is a UFT. That implies Z of X is UFT. But does not imply Z of X is PID. These two theorems are not easy to prove. It bit involved. The first theorem is bit involved. Second is even more tougher. I think we need Gauss lemma to prove them. Gauss only proved this. Very hard in a way, the second thing, but try to understand the statement is very easy. If underlying ring is UFD, the polynomial ring becomes UFD. If the underlying ring is UFD, the polynomial ring is UFD. That's it. That's the end. That's it. Okay. Okay, fine. So how this is going to helpful in my questions? There are a few questions I had at. So look at this question. Okay, not this question. I want. Yeah. Look at this question. Which of the following ring are principal ideal domain? This is 2017 June CSIR. So you can answer no this question. Let us answer first. A. Q of X. PID or not? Yes, no PID because the underlying ring. This is field. That's what that theorem says that in order to become that is a PID, the underlying ring should be field. What about this? Can you tell me? Z of X is field or not? The PID or not?
No.
Not PID.
Why?
Because it is not a
So the next one, Z by 6, that is a PID or not?
No.
Why?
Z6 is not a field.
So not a PID. Not a PID. Yes, PID. What about the D? Answer D.
Yes.
Why?
Z7 is free.
Yeah,
Sprite.
today we saw that ZP is field. As long as it is a prime, right? So very easy. You see that in CSR exam, always there are few questions. When you know the statement, you just go through just 30 seconds to minute to answer. You go through the questions. There are in NBHM, at least I can tell you, in algebra section, there are 10 questions to answer. There are always 3 questions are very easy. Just answer them. Momentum generation. You will get lot of energy, lot of energy left, lot of time left to attack the very hard question. But initially, they ask hard question, which requires a little bit of workout, and you may lose the time, and you will get sick of that. I am using lot of time. Then you will miss the easy question in the end. It's one of the trick in CAT exam in the institution level. They always tell the student attack easy questions. Whatever you feel easy, go through all the question. Don't read more time. Don't give more time in reading the question and writing the question. If you attack easy question in NBHM, in the first section, always 3 questions are easy. Attack them. You get the momentum. You get the timing. Once you get the timing, rest is easy, right? So this question is very easy. Just you have to check the underlying is ring or not. Sorry, I mean field or not. Okay, one more question I put. I forgot. Okay, let's do this question. Let R be the subring of Q containing 1, then which of the following is necessarily true? Is R is a principal ideal domain? Okay, they are saying that R is a subring of Q. Do we have example? Yes, we have example Z. Do you have any other example other than Z? Do we have another example other than Z possible? Do you know any other examples? Any other examples? Okay, suppose we don't have, let us try to attack with this example only. R is principal ideal domain. They're asking R is principal ideal domain. Is it true? What we think? What we have a feeling? First we have a feeling, right? As far as if you set, okay. So can you see some trivial rings? 0 is a trivial ring, but that's not possible because they say contains 1. So we have to have at least 1. So if the 1 is there, 2 will be there, right? If 2 is there, 3 will be there. So all the natural number will be there. So 0 will be there, of course, ring. All the minus rings. Suppose if you have a ring, automatically that consists of Z. Because 1 is there, 2 will be there, 3 will be there, minus of that will be there. So you have to think more than Z or less than Q. Do you have some example? Yeah, we do have some example like this. The smallest string containing integer and 1/2. The smallest string containing integers and 1/2. You may ask, is this not Q? Actually, it is not Q. The smallest string which contains an integer and 1/2, it is not actually Q. It is one of the ring. There are some rings like this, okay? So now let's have a discussion over this. There are a few questions about this, like R is a principal ideal domain or not. Okay, what do you think? Is it possible to have a principal ideal domain? I'm not going to do this question because I don't want to give you the answer, but I will give you the idea. We suffer to solve this question because we lack of examples. If you know about few examples, it's not hard. So the theory will bounce you as long as you know the example. If you don't know the example, the theory will not bounce you. So try to think about this example, try to find about this example, okay? But let me come back this question. People ask this question in a many way. Which of the following is not true? They say QS is PID, ZX is a PID, Z by 6 is a PID, D by X a PID. They will ask some questions, okay? Okay, fine. So one more example I wanted to finally talk about will give you the idea. In finite case, finite ID implies field. I proved it using the Homoouson technique. What about infinite? What about infinite? If all the infinite integral domain is field, not true, right? It's not true. Okay. Do we have integral domain and the field? There is a connection. Do we have anything between them? Actually, no. The integral domain, the next level is actually commutative ring. If you integral domain is slipped into field, that's why the thing. The another question, is there any ring not commutative but as all non-zero element in unit? Those are called division rings. Division rings, all the properties of field there, only the multiplication commutativity is not there. Do we have such example? Do we have an example of a commutative ring? Sorry, non-commutative ring, but it's almost field except the commutativity. Do you have example? Anyone knows about some example? Have you heard of some example?
The real quaternion.
What?
Real quaternion.
Nilpotent.
No. Real set of real quaternions.
Real quaternions. Very good. Yes. So he's saying that set of all real quaternions. This is the example. A plus bi plus cj plus dk such that a comma b comma c comma d comma belongs to real number I square j square k square equal to -1 I j. There is a beautiful picture I j k. I into j is k into I is j k when I multiply I. So when you multiply two of them, you will get that. But when you multiply reversely kj, you will get -I. That's what this means. So I power 4, j power 4, k power 4 equal to 1. So this is called real quaternion. This is an example of this is an example where it satisfies every function other than commutativity. Clearly, I told you, no, ij is k, but ji is actually -k. So it's not commutative by definition. You may ask me, why did I talk about this at this point of time at the end of the class? Because this is there in the video. In the group theoretical level, there is a quaternion group. I talked about it. There is a video about this in my YouTube channel, as well as I think I talked about in our class also. This is the third time I'm giving talk. Okay, this is the third time I'm giving talk. So it is there. So there is a group theoretical connection which plays a role in the ring theory. Okay, so that's what I wanted to understand. Fine. So let me finish at this point because of the time factor. Hopefully, I will give another talk later, where I will continue about the PIDs even better and go up to the polynomials. Okay, let me finish this class. I will share this PDF to Vinod sir and he will share in the group. Okay.
So that identity function is not a zero divisor you told. Can you briefly explain that again?
Yes. Okay. So let me share my screen. Okay. So you are asking about identity function. We are in the setup of C01, correct? So we are in the setup of C01. The identity function, which is not a zero divisor. That means identity function is this, no? So I like to prove this is not a zero divisor. To become not a zero divisor means what? If I multiply identity function with any other function, when I get identically zero, I like to prove this is not a zero divisor. So claim G is identically zero. If I multiply, I get 0. One of them not 0, other than also not 0 means it's a zero divisor. So I know this is not zero function because at 1 it takes 1, at 2, I mean 1 by 2 it takes 1 by 2. Only at 0 it takes 0. So it is not a unit. But I like to also prove this is not a zero divisor. Okay. So generally I multiply with a G, which is a not a, I mean when I multiply, I like to prove that G is 0. Up to this claim is clear to you?
Yes, sir.
Now how do I prove? When I put id of x, g of x, multiply g of x, by definition I'm getting identically 0 for any g. That's a definition. But this is like x into g of x. If x is not 0, where x coming from? Closed 0 to open, I mean closed 1. If you take x is not 0, that implies g of x is 0, no? When you put x is a real number, g of x 0, correct? For every x belongs to open 0, closed 1, correct? So that says that g is identically 0 on open 0, closed 1. Only thing I have to prove that to become a 0 element, it should be everywhere 0. It should be everywhere 0. Now the only problem at 0, what happens? At 0, what happens? Is it 0 or not? Question. Is it 0 or not? But remember that at 1 by n, g of 1 by n, because everywhere is 0, at g of 1 by n, what happens? This is 0. Now take the limit n tending to infinity. Limit n tending to infinity 0. N tending to infinity 0 is actually 0. There is nothing here. Here, because of the continuity, I can write like this. Because of continuity. What is this? G of 0. Because of continuity. Otherwise, it's not true. So G of 0 also true. That means G is identically 0 on closed 0. So G is everywhere 0. When I multiply some function with identity and I'm getting identity 0, that function is a 0 function, says that identity is not a 0 divisor. So to prove something is not a 0 divisor, what you need to prove? That if you multiply with something, that something must be 0 randomly, abstractly. So arbitrarily G is I multiplied and I showed G is not 0. Right? Now you understood?
Yes, sir.
Right. Okay. Next question.
Our resource person, Jayakumar, qualified CSAR JRF 2 times as well as NBHN, and he's almost to submit the PhD, and his research area is planar algebras, and he is doing his research under Professor 𝔸𝕗𝕤𝕒𝕦𝕤 of IMSc. So make use of this opportunity to ask your queries regarding preparations for competitive examinations, as well as about you can ask about the institute IMSc and all that. So make use of this opportunity. Please come forward.
I am Dharmendra Singh from Visakhapatnam. I want to ask how to prepare for and CSIR net and TFR also. And please tell your research experience also at IMSc. And I want to ask some resources about abstract algebra, including ring theory. Thank you, sir.
Okay. So the first question, how to prepare for these exams? Okay, right. So I like pure. Most of you maybe like pure. Then applied also there. So you have to find what is your strength or you like areas. If you are pure focus on algebra analysis, complex analysis, and linear algebra, there are very good books are available. One such book I personally use for teaching by Dr. A.P. Singh. Okay, I personally use that for teaching. Today also I get some few examples and other things from there only. Okay, but the great thing which I found, try to attend the talks, get the ideas. I used to attend. I don't like much to read, but I used to attend every week one section in IMSc. Few seniors used to teach me. Then I got interested in IMSc because IMSc is one of the great institutes where they don't charge anything. Basically, they don't charge anything. In IITs also, you have a charge every I think semester you have to pay certain things, which I found that IMSc don't take any money. Many good institutes, they don't take money and they give you opportunities. Like you go to the institute, stay there for 1 year, then you can choose. But if you compare to the lower institute, they will fix you. So you have to do in this area, you have to do in that area. Okay, that is a very good thing about institutes like IIT, institute like IMSc, TFR, and other things. So if you wanted to prefer, especially for TFR and IMSc, more or like things are same, you have to choose pure. In the pure also, you don't need to go for every subject. I love algebra first. I would say that since I like algebra, I choose to go IMSc. I don't prefer IISc at that time because when I was like preparing, IISc don't have algebra. If I like number theory, I would have preferred HRI, not IMSc at all. Okay. So you try to find it. How to find it? Now the question, how to find my thing? When you attend this kind of talk, you may get inspired over the people and you talk to them. Then you get the idea. Okay, this area may. Then you talk to them. Like you can ask me about algebra. I can share my algebra experience because I'm always fascinated about the structure. Then the physiological aspect, like action. I'm not a person like actually going for action, but I like to understand the structure. So I like algebra. And if you ask me, I will give you n number of institutes where algebraists are there and they are doing institute. Similarly, there may be a good person in analysis. They may give you some good idea and insight. From that insight, you can pick up what is your way. I'm telling you all. Once you've done that, then focus on that. And you will get it. IMSc have very rich culture in algebra. CMI has very rich culture in algebra. IISc has a very rich culture in analysis. IISc Kolkata, really, really excellent for analysis. IISc Bangalore, excellent for analysis. For number 3, IIT Bombay, HRI, both are really good institute. Terrific number theories are being presented there. So you have to pick up your list and preparing according to that. There are slight variation between the exam to exam, but most commonly you have to clear CSIR. Then only you can think about other exams, right? If you wanted to prepare for NBHM, focus on algebra, analysis, and topology. Keep attending these talks. You will get, a lot of good thing. Also, I see there is a very nice YouTube channel maintained by Vinod sir, and you can go and get it. In my YouTube channel, you can get a lot of things about algebra, especially group theory. But in that YouTube channel, I have seen people, various topics are being talked, and I have seen some interesting topic other than pure mathematics, which is inspiration, right? So you will get the idea. And to prepare, like, you have to focus first on that, okay? Then what is about the next question?
Sir, your research experience.
Oh, my research experience. Okay, so I picked up the very hard area. Hardly, I think in the world itself, only 50 people are doing. There is no book. It got introduced around 1993 or something, 1986. It got be proposed and really introduced around 1990s. Still, there is no book, okay? But that's a beautiful thing, right? You are somewhere like a pioneer. So that's why it takes little longer to finish. I have a paper like finished. It has to be like yet to send and something has to be done. But I knew that I wanted to do algebra. From the beginning itself, from my MSc itself, I knew that thanks to my seniors who conducted such classes, I knew that I wanted to do algebra. In the algebra also, particularly, I want to do about structures other than the actions. So I picked up planar algebra. I approached my guide. My research experience consists of a lot of teachings. If you see my CV, you will have a lot of teaching. I attend a lot of things, but most of them are algebra. So I always passionate about algebra. I visit people who are in algebra. I talk many people who are in algebra. So my research are more or like in algebra. So I don't know much about analysis, but although I am doing in the midway, if you ask me about analysis, I can tell you in the analysis perspective also. My thing in the midway. As long as soon as you find you wanted to do algebra and other thing, but one thing I can say, be open about research area. You like algebra. If you like really algebra, you will like topology, point set topology, and algebraic topology. You may not like a geometrical idea, but if you are like good with a geometrical idea, you will like certain things in analysis. So be open. That's much I would say. My research experience is really good. Now, up to now, I'm in the research. It's really good. Okay. Any other question?
Sir, your topic is under
Planar algebra.
algebra. What it mean by
Right.
planar?
Okay, so
And
very good question. It's what about my research area? My research area is consists of non-commutative setup of Galois theory, one can say. Okay, in algebraically speaking, it can be studied in analysis way and algebraic way. To make you understand, Galois theory, somewhat you are connecting the polynomials with a group and trying to understand them, right? You're trying to understand them from the group theoretical perspective. The group is helping. What I do is called a non-commutative setup of Galois theory. So in the field, instead of field, we study about the subfactors. Field extension, there are two things, right? Subfield and the superfield, we are trying to understand. My area, we are trying to understand about subfactors. There is a factor and there is a superfactor. The lower factor works as a subfactor. We attach planar algebra. What are the information we can get out of the thing from the this planar algebra, right? So this planar algebra has a lot of things. From algebraic perspective, you know this minus b plus or minus root b square minus 4ac by 2a. This quadratic formula works. There is a formula for cubic. There is a formula for degree 4, quintic. But pentic is not. From degree 5, there is no possible. This is due to Galois, and this is due to the S5. From S5, the A5 is being simple. In the group theory, S5, S6, S7, the A5, A6, everything becoming simple. Before that, that is not true. That's the connection. So Galois proved that it is not possible to have such a nice kind of function where you can solve 5-degree polynomial, general 5-degree polynomial. General 2-degree polynomial you can do, 3-degree you can do, 4-degree you can do, 5-degree it is not possible. So that means you cannot write algorithm. It is worthless to search an algorithm for computer. If you put the computer 2-degree polynomial, it will find the answer. That means there is a possibility of algorithm. Galois proved there is no algorithm can be find in this way. So you have to search in a way. So that's why new techniques are coming. Algebraic number theory. There is an area of algebraic number theory which I don't much interest, but there are people who are interested. Simply they are trying to understand the extensions of Q. Q is their base field. They called any extension of Q, they called algebraic number field. Okay. Many things are now done in that area. People are going. So my area is non-commutative setup of Galois theory from algebraic point of view. For analytic point of view, it is trying to understand certain analytical group of functions in a much understandable way, where there is not an analysis function catching through algebraic tools. So that's why it's a little tough. Not too tough.
Okay, sir. Yeah, thank you, sir.
Okay, thank
Sir,
you,
please
Dharmendra.
tell some. Please tell some reference book also.
Yes, I will tell in the finally about what I do. I will tell the reference book. Okay, at the final I will tell.
So thank you, Dharmendra.
Thank you.
Others, please feel free to share your opinions.
You can share your opinion, please, about the class. If you find toughest, also you can tell. Sir, I think you get muted.
Yeah, Archana.
Hello, sir.
Yes.
Yeah,
Tell.
Vishwajit.
Good afternoon, sir.
Yes.
I'm Vishwajit from Mumbai. I've completed my third year this year. Actually, I was solving questions and
Could you
on
switch on video, Vishwajit?
it is not possible. Okay, sir. Hello, sir.
Yes.
It's nice to meet you, Vishwajit.
Yes. Yeah. It's better to have eye contact.
Okay, sir. So, like, I was solving a question on ring theory, and I found one question like, if I have A and B in a ring, so that AB is a zero divisor. Does it imply that BA is also zero divisor?
Yeah.
What the main problem I was facing here, like that, when you define the zero divisor, there we have to the A is non-zero in a ring, and it is said to be zero divisor if we get some non-zero B such that AB is zero, right?
Right.
But in that book, they haven't taken initially that A should be non-zero.
Yes. So it depends on the book. Book to book they talk. Okay. So this is very unfortunate that certain books, for example, in generally India, in the lower institutes, they follow I.N. Erskine. This I.N. Erskine book, they follow. Many teachers studied from I.N. Erskine. Unfortunately, I.N. Erskine never talked about anything relevant to group actions. But modern theory only deals with group action. So somebody asked me about my research area, right? In my research area, how 2-1 subfactors acted by a exterior group. In the representative theory, how this is acted by that. Linear algebra, GLN of V, that is invertible matrix. How invertible matrix acts on the vector spaces. So unfortunately, books have some views. If you take a Galilean book, they will treat differently about Sylow's theorem. They talk about Sylow's theorem in a different way. Whereas Damit and Food, they talk about different way. Artin talks about different way. So I would say that if you want to go for modernization, nowadays people follow this definition. They take A non-zero and they go for that. So that's why you have to be very consideration. So I will tell you, I faced one problem when I was in an NBHM exam. If you follow I.N. Erskine for SN, how to compose it through two permutation. Older way of composing is American way. American compose from left to right. But what we do for a function case that f composes g at x, first you do g of x, then f of x, right?
Yes, sir.
That's we use. Now that's why we go from left to right. I mean, sorry, right to left. They go from left to right. That's why it's a bit confusing. So better to use books like 𝔸𝕗𝕬𝕐𝕗, 𝔸𝕗𝕐𝕗.
Okay. Like the
Right.
then if I assume that a to be if I consider 0 as a zero divisor there, then it was not possible for me to find such an example which in which
Yeah.
this situation doesn't.
That's why we trivially like avoid. We don't want to that. That's why 𝔸𝕗𝕬𝕐 is very dictionary. So 𝔸𝕗𝕬𝕐 is kind of named as a dictionary for abstract algebra. Remember, okay, Dharmendra, you asked, 𝔸𝕬𝕐 is like a dictionary. 𝔸𝕗𝕐𝕗 is like an exact book. 𝔸𝕬𝕐 is like a dictionary. 𝔸𝕗𝕬𝕐 abstract algebra is a dictionary for algebra for
Okay,
everybody.
thank you, sir. Sir, one doubt was there. Like you said you are teaching and you are doing also PhD at the same time. How it is possible, sir?
I'm not able to understand what is the question really.
Like you are also teaching, sir, and you are also doing your PhD. So you are doing
Right.
both the things at the same time.
What is the question? My PhD, what?
I'm saying like
My,
during PhD, sir, we have to give full time, na, in IMSc.
yes, no need to go IMSc regularly, but you have to be there at the meeting. It's better to be there. They will give you office and other thing. It's better to be there. All the resources, and you see all the people are studying, you will also get a study mode. But if you are in home or somewhere else in the hostel room, it's not easy to get yourself right. So that's why it's an office type environment always better. But in IMSc, there is no something called attendance is necessary. From second year onwards, it's like you and your PhD. You no need to
Okay.
be there as presented. As long as you are.
Yeah, actually, Jay, I would like to add one thing. The Vishwajit who asked question last, I take this opportunity to congratulate him. He's scored JAM All India rank 2
Super.
and got
Very good.
got admission for integrated PhD in TIFR camp.
Super. Bangalore. Nice.
Yeah.
Good. Congratulations.
Vishwajit, are you there? I think.
Thank you, sir.
Yeah.
Yeah, I actually there is a person who joined in a TFR camp. His name is Shiva Guru. He is doing several complex. Initially, it was available only in IAS. It's like a IASC thing. Now many people are doing in IIT Palakkad. There are 2 people are doing. I think in IIT Bombay are doing. That area is very emerging. So if if you meet that person, say hi from my side. Just tell Jayakumar said hi. You can talk to him, and he's very new, and this area is very emerging. If you like analysis, one of the best place to do that area is one of the best place to do. In IASC now there are 2% plus one more joined. So it's a very vast area now in India. Several complex analysis.
Okay. Any others? Archana, you have started to say something. Okay.
Sir,
Yes.
my name is Archana.
Yes.
I am from
You're
Kerala.
from-
I completed IMSc and I have difficulty in doing problems from string theory. But today's session was very useful for us, and especially the problems on C01. And it was very interesting and useful, sir. Thank you, sir.
Thank you.
Thank you, Archana. Others? Okay, dear participants, please share your opinions or your views. Feel free to switch on your video and speak.
Hey, I am student still, not having any internal thing over you people.
Don't miss this type of opportunities.
Hello,
Yes.
sir. I'm Malika. I'm
Malika.
a graduate student from Kerala. Thank you so much, sir, for this wonderful session. The class is really nice. Actually, for me, group theory is one of the most difficult topic. But today I get to know about a variety of new things. Once again, thank you so much, sir. And also, we are expecting more classes from you.
Yes, I would love to do that. Okay, like I will do. My idea is 10 classes I will do some sort of overview of algebra. Group theory 2 classes done. Ring theory 2-3 classes will be done. Then my idea is to do the Galois.
Okay, sir.
Then that will be a contribution myself, but I will do it over the period.
Okay, sir. Thank you, sir.
Thank you.
Okay, thank you, Malavika. Others?
Yes, I will share my email ID.
Yeah, we can share it along with the recording, and also the PDF can be shared.
Right.
Is any others? Students, feel free to speak. Yeah, Fatima. Yes.
Hello, sir. I'm Fatima from Kerala, studying in Associate College, Tirur. I'm third year BSc Math student. So thank you, sir, for this wonderful opportunity. The concepts are very clear. I've clearly understood everything, and we are looking forward for your more classes, sir. Thank you very much.
Thank you. So you're from BSc, right?
Yeah, BSc. I'm still in third year student, but still, I've just started the group theory topics.
Right. Okay. When you come to ring theory, you will get it more. Yes.
Okay,
Yes.
sir. Thank you,
Yeah.
sir. Thank you.
Someone Zainab. Yes.
Hello, sir. I'm Riza. I'm also from Kerala, doing my third year BSc Mathematics. Thank you very much. Thank you very much, Jaisa, for putting your effort and time for this helpful session. I was not very much. I really don't know about this topic, but I am first to this topic. But your session was really helpful and understandable. Thank you very much, sir. Also, thank you very much, Vinod, sir, and Math Aspirants team. Thank you.
Thank you.
Okay, thank you, Risa. Okay, dear participants, feel free to switch on your video. It will be nice to
get to know.
Yeah.
Yes, sir.
Yes.
I'm Zahra Armaisa from Kerala, TMC College, Tirur. And thank you, sir, for this wonderful session. It's very useful. And thank you, Vinod, sir, for conducting this session. Thank you.
If any of you would like to express any views, please do it now.
Yeah.
Otherwise, we will wind up the session now.
Right.
Yes.
I'm open up to criticism also. You can tell about, So last time I remember that two BSc students said that they don't understand certain things, but they're looking forward it. That's what it is. For BSc student, little push-up needed, right? And we wanted to say certain things which they come across later. So they used to keep their interest. Otherwise, they may lose the interest. The real problem from our side, we may lose a good student who is sincere. So you see in the Sunday, right? In the Sunday afternoon, you don't go or rest or go away. You're spending 3 hours here means it something sincerity. So we don't like to lose the sincere students, right? Okay, then. So yeah, 1 or 2 more questions would be feedback will be nice.
Yeah. Yes. Any others? Yes, Lakshmi.
Hello, sir. I am Lakshmi. I am from TMC College, Tirur, Kerala. Today's class was really nice, interesting, and very informative. You explained each topic very clearly. Thank you, sir, for spending your valuable time with us. And thank you, Vinod, sir, for conducting this class. Thank you.
Are you a BSc student or MSc student?
Sir, BSc.
BS. Very good.
Okay. Thank you, Lakshmi. I think there is no one to almost over. So let us wind up here. Once again, I would like to thank Jay for being with us and expecting your cooperation in future too.
Yes, definitely.
Yeah. Thank you once again. Thank you very much. So let us wind up here. Thank you, everyone.
I am sharing the thing in the Telegram, sir, to you.
Okay.
So we know.
Yeah.
Yeah, because WhatsApp is not connected to iPad. I'm sharing to those. Please share the video.
Yeah. You can share it me in Telegram. Okay.
Shared.
Okay. Thank you.
Okay, sir. Thank you. Thanks for a wonderful opportunity. I will come. I think I am not a new. I mean, last two classes I said thank you, and I think I am a part of this. No need to say thank you. I wanted to give regularly. I would say that in a month at least one class I wanted to do.
Yeah, actually, you are one of the main part of our Math Aspirants team, and it should be. And see, our group is running through all these with the help of these research scholars and young faculties. Otherwise, I can't do anything. All these are a collective effort.
Right.
Okay,
So
once
as a
again,
part of that, if I say thank you, I think I will say thank you to myself in a circle. So I don't like to that. I look for the other things. Okay.
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 Okay. Let us sign up here. Once again.
Bye.
Sweet. Okay. Bye.
Bye.